Hello, AP Chem students, and welcome to topic 7.6, Properties of the Equilibrium Constant. The learning objective for today is 7.6.a, represent a multi-step process with an overall equilibrium expression using the constituent K expressions for each individual reaction. So, basically, this relates to some of the same ideas that we've been using with Hess's law and reaction mechanisms. So when we manipulate a reaction to make it sum, to give an overall reaction process from reactants to products. So specifically when we're looking at elementary steps or elementary reactions, we can manipulate the K to reflect that change. So modifying the chemical equation in certain ways can lead to predictable changes in the K. So for these examples, we're going to consider this original reaction. We've looked at this kind of model reaction before. And so therefore the original K is going to be, again, the products raised to the powers of their coefficients over the reactants raised to the powers of their coefficients. And so we would be assuming here that all these species are either aqueous or gas. If the reaction is reversed, then it should make sense to you that what happens is we invert your K. And again, that should make sense to you because instead of what was the products is now the reactants and vice versa. And so we just switch for the K. And so if you know a numerical value for this, then that is mathematically equivalent to doing 1 over your K or the inverse of your K. If the original reaction is multiplied by some factor n, whatever that might be, 2, 3, 4, a half, any of that, so that all of your coefficients are multiplied by that term, then you're going to take your K and raise it to that power. Now, if you stop and think about that, that's because when we multiply the coefficients by a term, then in your equilibrium expression, that means that we're changing the exponents to be a multiple of that term. And so that's why we raise the value of K to that exponent. So for example, if this was 1 and this was 2, and then you multiply it by 2, then this is now 2 and 4, then what was 1 and 2 in your, in your denominator down here are now 2 and 4. And so that's how that impacts your K value. When equations for individual reactions are added to give you an overall equation, we multiply the K values. And so that looks like that. And that's, again, because what we've done there is we've taken reactants and products for 2 individual reactions, and now they're combined. And so by having a K expression for the one and a K expression for the other, then we can just multiply those values together. And that would be the same as combining them into one K expression, because we would simply be adding on, we'd be taking all of your products and putting them in one denominator, numerator, and all of your reactants and putting them in one denominator. And so that is mathematically equivalent to just multiplying your K values. This makes more sense if we think about it in terms of an example, which I'm going to show you in just a second. Because Q and K are mathematically identical, anything you do to K, you can also do to Q. So if you know the Q and then you do something to the reaction in a predictable way, then you can manipulate your Q value in exactly the same way we would manipulate K. Okay, so let's look at this practice. So the following equilibrium concentrations were observed for the Haber process at 127. This is the Haber process up there. And so then you've got these mathematical, or these concentrations, excuse me. So you're going to A, calculate the value of K to start with at 127 degrees Celsius for this reaction. Then calculate the value of the equilibrium constant, 127, for the second reaction. And then C, calculate the value of the equilibrium constant at 127 for this reaction. My arrows dropped out of those last two reactions, but I know that I did add them back in on the next slide. So if you want to go ahead and try this on your own, please pause the video now because I'm about to go through the answer. Okay, so here's your question, and I've gone ahead and included your K expression here. So as a reminder, we do products over reactants, and then we raise the concentrations to the power of the coefficients. And so you should be getting good at that at this point because we've done that several topics now. So the next thing you're going to do to calculate your value of K, and again, this is from the previous topic, is you're just going to plug in the values given to you in the problem because it told us that these were the concentrations at equilibrium. So we'll plug in like so, and then we'll go ahead and do the math, and you end up with 3.8 times 10 to the 5th. As a reminder, K is unitless, okay? So now we're going to calculate the value of the equilibrium constant 127 for this new reaction. So what we've done is we've reversed the reaction. So we flipped it. So what was the reactants are now the products and vice versa. So remember that when we do that, all we have to do is we have to do 1 over k. So we're going to do k prime is equal to 1 over 3.8 times 10 to the 5th. And that is 2.6 times 10 to the negative 5th. All right. And then in part C here, we're going to calculate the value of the equilibrium constant at the same temperature. Important that we're staying at the same temperature here for this reaction in part C. What we've done here is compared to the original reaction, this reaction has been halved. And so we're going to do, that is a boo-boo. So I'm going to pause this and fix it. Hang on. Okay, so that's better. So the reaction has been halved, and so to find k double prime here, we're going to take the original k and raise it to the 1/2 power. So then when you do that, it's going to be 3.8 times 10 to the 5th. Again, remembering to come back to the original value, we're going to raise that to the power of 1/2, and then you get an answer of 620. Now, actually, when you do this math, you get 616, but point out here that we've got 2 significant figures in our prompt, and so we need 2 significant figures in our answer. And again, a final reminder that k is unitless. That is how we do that. So what should you be able to do with this? Sorry about the bell. You should be able to manipulate the value of k to correspond to a manipulation of the reaction it represents. And that is it for this learning objective. And I will see you soon for calculating equilibrium expressions.